Hi, welcome to our talk on conditional cuckoo filters, approximate set membership with predicates. My name is Daniel Ting, and this is work with my colleague Rick Cole. So in this paper, we consider a variation of the approximate set membership problem. And in the basic problem, you have a single large set S drawn from some even larger domain. You want to summarize it into a small data structure, i.e. a data sketch, which is able to answer a question, given an item or a key X, is X in S? And this data sketch will allow for some probability of a wrong answer in order to be able to store it in an extra small amount of space. These sketches have proven useful in many applications since they often allow avoiding unnecessary expensive operations because of the one-sided nature of their error. There are no false negatives, so that if the sketch says that an item is not in the set, often you can avoid the expensive operation. And you're probably familiar with sketches that address this problem, which these sketches include Bloom filters, Cuckoo filters, and quotient filters. So we're interested in a problem where we have not just one set of interest, but many sets. And these arise quite naturally in databases. Any database query that you execute, whenever you change the filter conditions, the resulting set of items that are returned is often different as well. So now, rather than representing a set of keys, we want to represent a table of non-unique keys along with their attributes. We want to be able to query for just a key or a key plus some equality predicates. And this will answer the question, is there a row in this table with key K matching the given predicates? And we want to have all of the usual benefits of sketching, which is that we want to build a sketch in one pass to be able to have fast queries and no false negatives. So concretely, how might such a sketch be used? The motivating example we use is that in join processing. Suppose you have multiple tables that you want to join together, all on the same ID, and where each table has a selection predicate applied to it. When you're processing the join, whenever you're scanning a table, ideally you'd be able to use information from all the other tables to restrict the intermediate outputs of that scan. However, if I were to use a Bloom filter, it can sometimes be useless. For example, in this example over here, where we're joining three tables about movies, each of the tables essentially contains all movie IDs. Every movie has a cast, every movie has some company associated with it, and every movie obviously has some title. So if I were to apply a Bloom filter from the other tables, when I'm scanning, say, movie companies, these Bloom filters essentially filter out almost nothing. However, if I am able to apply predicates to it, the set of IDs for the titles and the set of IDs for the cast become much, much smaller, and I'm able to get a sort of multiplicative effect in reducing the size of the intermediate outputs. Now, if I were to try to use a Bloom filter to accomplish this, where I have some pre-computed sketch for each predicate, then there's simply too many to store. Furthermore, if I tried this, I'd essentially be repeatedly storing the same key over and over, so the sketch would also be quite large, or the collection of sketches together would be quite large. I could take another approach, which is to build a Bloom filter on the fly. That is, at query time, I scan all three tables to build Bloom filters at runtime. But this involves some extra work and communication costs, and the information that's in the sketch would not be available for query planning purposes. So our idea is to build a filter that just supports predicate queries. And how to do this is quite simple. So what we do is we notice that Cuckoo filters are essentially the same as Cuckoo hashes, except for the key value pair, we remove the value and we replace the key with a key fingerprint. So what a conditional Cuckoo filter does is essentially add back that value as a sketch of the attributes. In this case, the challenge is that keys in a conditional Cuckoo filter are not unique, while they are unique or very close to being unique for Cuckoo hashing and Cuckoo filters. So in this paper, we go through several options about how to sketch these attributes. The first option is the simplest, which is to sketch the attributes as a Bloom filter. So in this case, if we have a table, we have several attribute tuples, we essentially convert these tuples or the individual entries, attribute entries, into attribute name, attribute value pairs. And in doing so, we can construct a set of these pairs. This allows us to collapse multiple rows into one, so we don't have to deal with this kind of multi-set problem of having duplicate keys. And we can make this set basically as large as possible, right? So the sketch has infinite capacity. It's just that the false positive rates get worse as you add more and more items to it. And some of the disadvantages of such a sketch are pretty obvious. First of all, it can't capture any dependence across columns. So if I were to query for the movie Harry Potter and ask if there's a predicate that matches Emma Radcliffe, then it'll return true even though there is no such Emma Radcliffe. There's just the actors Daniel Radcliffe and actress Emma Watson. Second disadvantage is that you can't resize the filter. As you get more copies of a key, you typically get more of these more of these distinct attributes, and so the false positive rate just keeps getting worse and worse. Another option is to just sketch each attribute entry individually. So in this case, I end up with a table of the same structure. It's just that each entry takes up much less space. In this case, we also need to store multiple copies of a key fingerprint, and there could be quite many of them. A third option is to take a hybrid approach. We can switch from this sketch of each attribute to a Bloom filter when we encounter too many duplicate keys. And in doing so, we can keep using just typical Cuckoo filter, which can support a few duplicates, but not too many. So if we were to implement a Bloom filter or this hybrid option, they're relatively straightforward. You just use whatever capabilities the Cuckoo filter can support. And since it can support a few duplicates and some deletion, then these are both okay options. The more challenging case is when there are many duplicates. So before we get into how that's done, let's first briefly review Cuckoo filters. So a Cuckoo filter is essentially an array of key fingerprints, a two-dimensional array where the rows denote buckets in the filter and the columns are the entries in the buckets. Whenever I hash a key, or whenever I insert a key, I hash the key to two candidate buckets. If one of the candidate buckets has an empty entry, then I'm able to directly insert it into that entry. However, if two buckets are full, what I need to do is I need to kick out one of the existing entries to make space. This allows me to insert my new key into it. But the key that I kicked out needs to be inserted into its alternative bucket. And so now I just repeat this process of kicking out and reinserting until I find an empty spot. The advantage of doing so is that I only need to probe 2 buckets per query. So this both helps with the query time processing, that I can get constant time queries, and it keeps the false positive rate bounded. The other nice thing is by doing this repeated kickout procedure, the insertion has a high probability of succeeding until the load factor is actually quite high. The problem with this approach is that you can't store many copies of a key. Since there are only 2 candidate buckets, and if each bucket contains at most B entries, then you can store at most 2 B copies of the key. So you're likely to fail with a low load factor when there are too many duplicates. So how do we add more duplicate keys? So we introduced this idea of chaining, which is to add more bucket pairs whenever one bucket pair contains too many copies of a key. If it doesn't contain too many copies, then we can just perform the normal insertion or kickout operation. This essentially provides a method for adjusting the amount of space that's allocated for a particular key as it encounters more and more duplicate copies. And there are 2 ingredients to defining this chaining procedure, one which is the rule to find new buckets. And the second is how to determine what the new buckets are. As for when, we find a new bucket pair when there are already d copies of a fingerprint for some constant d. This ensures that the filter can reach a high load factor, since no key can dominate a bucket pair. And it makes it so that the number of bucket pairs probed can adjust dynamically. You only need to look for another bucket pair at query time if you find that the current bucket pair that you're looking at has d copies of a fingerprint. As for how to select the next buckets, you chain buckets by computing the next bucket pair as a function of the current bucket pair and the key fingerprint. So specifically, we take a hash of the minimum of the two bucket locations and the fingerprint key. The second bucket is just obtained from the usual partial key cuckoo hashing trick. And we do a third thing, which is to set a cap on the number of bucket pairs, or equivalently, the maximum space allocated for a key. Once we've reached this maximum space, any further insertions for that key are discarded, and at query time, any query involving that particular key, regardless of the predicate, will return true. So pictorially, it looks like this. I want to insert a pair which contains key 1, and we already see that the sketch already contains 3 copies of this key, or basically half the entries for that bucket pair. Since it's reached sort of the maximum number which I'm allowing for, I'm going to go look for a new bucket pair and insert it there. In this case, we find some empty entries and we can stop. If we didn't encounter 3 copies of K1, then we would have just inserted it directly into the first bucket pair. By doing so, we can achieve good load factors. So in this particular simulation, we try to insert keys multiple times. The number of times we insert each key is distributed as if Mandelbrot distribution, so a heavy tail distribution. And if I were to try to do this on a normal cuckoo filter, it fails almost immediately. The load factor at the time of the first insertion failure is nearly 0. But by using chaining, we can allow the sketch to achieve high load factors. So in this particular case, when we allow a sketch to a particular key to occupy nearly half the entries in its bucket pair, then we can achieve a load factor of roughly 75%. If we let it only occupy 1/4 of the entries in a bucket pair, then we get a load factor of about 90%, which is close to what you would get with a normal cuckoo filter. Or a normal cuckoo filter which doesn't deal with any duplication. So we can analyze the false positive rates for these sketches. The general formula for the false positive rate for both the conditional cuckoo filter as well as the regular cuckoo filter is to bound the false positive rate by the number of entries checked times the probability of a collision in each of the entries. So if I query for only a key, the false positive rate of a conditional cuckoo filter is roughly the same as that of a cuckoo filter. That is, it's bounded by 2b, so the number of entries in the bucket pair, times the load factor for the sketch, times the probability that any 2 fingerprints collide. And the reason for this is that you only need to check the first 2 buckets to verify whether or not a key is in the sketch. All of the duplicates are basically just handling the attributes. If I query for a key plus a predicate, then there are 2 cases. First is, if the key doesn't exist in the first place, then at worst the false positive rate is the same as that for a key-only query. If the key doesn't exist in the data, then the false positive rate is going to depend on both the data and the query. It's not a single number attributed to the sketch. If there are more unmatched predicates in the query, then the lower the false positive rate, but the false positive rate degrades as you add more and more duplicate keys. And there are 2 reasons for this, which depend on the type of attribute sketch you use. For the Bloom filter sketch, the probability of collision goes up as more attributes are added to the sketch. However, the number of entries that are checked remains the same. If we use chaining, the number of checked entries goes up, while the probability of a collision remains the same. And this is also another one of the reasons that we cap the maximum length of the chain, since as you add more and more duplicate keys, the false positive rate is getting worse anyways, at some point we just go ahead and stop. And so the space savings for this sketch really comes from two reasons. One, which is that the attributes themselves are compressed, but the second is that we're truncating heavy hitters in the data. And we can use this formula to predict the false positive rate. And for the examples that we considered here, the estimated false positive rate does a pretty good job of predicting the actual false positive rate, and it tends to be a little bit higher, so it's kind of a probabilistic upper bound. So we can go back and look at our motivating example. In this example, we are joining three tables together, and a valid query plan would be to first scan this movie companies table and build a hash table, do a hash join to the cast info table, and then finally do a hash join with the movie's title table. And in this process, I get a set of intermediate results. From the initial scan, if I'm not able to use the information from the other two tables, I may get a large number of tuples returned. Ideally, I would like the tuples that are in the intermediate results to just be restricted to the ones which will affect the final result set. But I can tolerate some number of false positives, which is roughly on the same order in size as this ideal number of tuples. Once I've applied a predicate pushdown, the intermediate results automatically get this benefit. You don't need to, again, use any sort of filter to get this savings. And finally, you get a final result set, which you're guaranteed is correct because the filters never returned any false negatives. So we can measure the performance of the benefit of the conditional cuckoo filter by just looking at this first initial scan. And we define a quantity we call the reduction factor to be the number of tuples that you return in the intermediate results when you use a conditional cuckoo filter divided by the number of tuples you would get if you didn't apply any filter. And so we take a look at the empirical results for the join order benchmark light. This benchmark uses the IMDb data, and the light benchmark chooses only columns with integer values. These are all categorical except for the year where there are some range queries. So for the range queries, we bin the year column in the sketch. And what we find is, compared to storing basically a full hash table, we use 1/10 the space, or roughly 1/10 the space. And we get a significantly better reduction factor than the plain cuckoo filter. So a plain cuckoo filter gets a reduction factor of around 0.7, which removes about 30% of the rows, while we get something which is closer to 0.3, or removing 70% of the rows. And what you see is that this is actually quite close to optimal, so we can't do much better than 0.3. The false positive rate in this particular case is roughly 1/9, so around 11%. And what we actually find is, even though we're already fairly close to optimal, most of the gap between the conditional cuckoo filter and the optimal reduction factor is actually mostly due to binning and not the conditional cuckoo filter itself. So in some sense, we might even want to size these sketches to make them even smaller, because it may be an appropriate trade-off to increase the false positive rate in the interest of space. And we also observe is what you might expect, which is that in cases where you're performing more joins, you get a more benefit in this reduction. And it continues to get better with the number of joins. There's this kind of multiplicative factor in this improvement in reduction factor. So in conclusion, we've introduced an approximate set membership sketch that supports queries with predicates. We've introduced a chaining mechanism that supports inserting lots of duplicate keys and adjusting the space allocated to a key. We've analyzed the false positive rate for the sketch, and we've demonstrated potential usefulness for the sketch in joint processing via predicate pushdown. Okay. Thank you all for your time.